In this exercise, we will build a sequential PLC ladder logic program in TIA Portal version 16 to manage an automated feeding cycle. The system is designed for a specific real-world constraint. It should only dispense food when a sensor detects physical movement in the water. Once that movement is detected, the program must trigger a precise sequence. Valve 1, Valve 2, and Valve 3 will each open for exactly 5 seconds, one after the other. After the third valve closes, the system is required to pause for 15 seconds before the loop is allowed to reset. To begin the configuration, open TIA Portal and create a new project. Developing this program requires a combination of timers and interlocking contacts. Coordinating these 3 valves provides a practical template for managing any series of hardware actions that must occur in a specific order. We'll start by defining the system's inputs and outputs. In the project tree, navigate to the PLC tags folder and open the default tag table. Add 2 inputs to the table, one for the manual start button and one for the motion sensor. Next, add 3 outputs to represent the hardware: Valve 1, Valve 2, and Valve 3. TIA Portal assigns these addresses sequentially. You'll see Valve 1 start at address Q0.0, with the subsequent valves following in the next available slots. Mapping these physical points to digital tags is a necessary first step, ensuring the software can communicate with the hardware before we write the logic. With the tags established, open main OB1 to begin building the ladder diagram. On the first rung, place a normally open contact for the start button, in series with a normally open contact for the sensor. Assign the output coil of this rung to a memory bit, M0.0. This M0.0 bit serves as a system running flag. Because the contacts are in series, the system only becomes active when the operator provides a start signal and the fish trigger the sensor simultaneously. Use M0.0 to trigger a 5-second pulse timer for Valve 1. On branch 2, place a normally closed contact for Valve 1 before Valve 2's timer so it waits. Valve 3 requires normally closed contacts for both previous valves to be off before starting. These normally closed contacts are essential. Without them, the timers for all 3 valves would receive a signal at the same moment, causing them to dispense food simultaneously. Using the state of a previous output to block the next step is a reliable way to enforce a strict sequential order in any PLC program. To make the system repeat, we need a final branch triggered by M0.0 that controls a second memory bit, M0.1, which will act as the reset. The duration for this reset timer requires us to look at the total elapsed time of the entire cycle. This timeline breaks down the requirements. We have 15 seconds of total dispensing time, followed by the 15-second mandatory wait, totaling 30 seconds for a full cycle. Because this timer begins counting the moment the system starts, set the reset branch timer to exactly 30 seconds. To complete the loop, go to the first rung and insert a normally closed contact for M0.1 directly before the M0.0 coil. When the 30-second timer finishes, M0.1 will pulse, opening the circuit on rung 1. This momentarily drops the M0.0 signal, clearing the timers and allowing the sequence to begin again. This self-interrupting logic creates a loop, allowing the program to repeat the sequence without further intervention from the operator. To test the program, start the simulation and load the project into the virtual CPU. Turn on the monitoring glasses to see the live status of your rungs. Open the PLC Sim simulation tables and load your project tags into the list. You may notice that clicking the Start button in the table doesn't immediately activate the valves. This is because our logic requires 2 conditions. You must also toggle the Sensor tag to simulate the fish movement we established at the start of the exercise. Validation in a digital environment is only effective when we replicate the real-world conditions the program is designed to handle. Once both conditions are met, you can observe the output tags turning on and off in 5-second intervals within the simulation table. After the valves finish their sequence, you'll see the 15-second pause before the reset bit triggers, causing the entire cycle to restart. To build on this logic, try adding a counter to the program. Set it to track the number of cycles and stop the system automatically after 3 full feedings. You can also try integrating an emergency stop tag. Program it so that it can break the M0.0 circuit at any point, immediately closing all valves regardless of the timer status. Mastering these basic timers and interlocks is the first step